How does plastic deformation break materials? Imagine bending a paperclip back and forth until it snaps. That's a simple example of how plastic deformation can lead to breaking a material. When materials are stressed beyond their elastic limit, they undergo permanent shape changes. Unlike elastic deformation, where the material springs back, plastic deformation causes irreversible atomic and molecular shifts inside the material. These shifts weaken the structure over time, making it more prone to breaking. At the microscopic level, plastic deformation mainly happens through the movement of tiny defects called dislocations within the crystal lattice. Think of dislocations as tiny lines or faults in the orderly arrangement of atoms. When stress is applied, these dislocations move, allowing layers of atoms to slide past each other more easily. This movement makes the material change shape without cracking immediately. There are two main types of dislocations: edge dislocations, which look like an extra half-plane of atoms sticking out, and screw dislocations, which twist the atomic layers in a helix shape. When the stress exceeds a certain point, dislocations multiply and move faster, causing more permanent deformation. As this process continues, the material's internal structure becomes more disorganized and weaker. This weakening can cause localized areas of high strain, which are spots where cracks can start. Over time, these cracks grow larger, reducing the material's ability to hold weight or resist forces. When cracks become big enough, the material finally breaks apart. In ductile materials, this process involves a lot of deformation before failure, giving warning signs. But in brittle materials, failure can happen suddenly with very little warning, often without much plastic deformation beforehand. In plastics and polymers, plastic deformation involves the chains of molecules sliding past each other or disentangling. When stress is applied over a long period, especially below the yield point, polymers can experience creep, which is slow, time-dependent deformation. This process happens because the intermolecular forces holding the chains together, like van der Waals forces and hydrogen bonds, are overcome. When these forces weaken, the chains slide past each other, causing permanent distortion or cracks. This is why plastics can become brittle or crack after being under stress for a long time. In real-world applications, plastic deformation is a key reason why materials fail or break down. For example, metal parts in machines can warp or develop cracks after repeated use. This deformation weakens the part and can lead to sudden failure if not detected early. Understanding how plastic deformation causes materials to weaken helps engineers design stronger, more durable products. They can choose better materials, control stress levels, or improve manufacturing processes to prevent premature failure. So, in essence, plastic deformation acts as a silent process that gradually erodes a material's strength until it finally gives way.